Alright, thank you for watching, and I got a bunch of requests for me to solve partial differential equations. So I was like, sure, why not? Let me solve the simplest PDE there is. Maybe not the simplest, but maybe the most interesting one in my opinion. Namely Laplace's equation. And you might say, hey, why is this the simplest? Usually in linear algebra and differential equations courses, you solve the heat equation first and then Laplace's equation last. It turns out theoretically Laplace's equation is actually the easiest one to solve. So let me do that. And what is Laplace's equation? It's just the equation Laplacian of u equals to 0. And you might say, what is the Laplacian? Okay, what is life? Well, that's the same thing as saying, take all the second derivatives in the sense ux1, x1, ux2, x2, ux3, x3, up to uxn, xn, and add them up. In other words, the second partial derivatives of the same order, ux1, x1, ux2, x2, etc., up to uxn, xn, where x is just x1, blah, 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 xn in Rn. And the question is, well, which functions satisfy that if you take this weird operation, in the end you get 0? And this suggests a certain kind of equilibrium, like saying that sort of the second derivatives are 0, at least of the same order. And in fact, Laplace's equation is used to calculate like the density of a fluid in equilibrium. But again, that's physicsy. Let's focus on the math. And just as in ODEs, etc., it's useful to find maybe easier kind of solutions. Or if you want solutions with a certain kind of symmetry, because, for example, in second order differential equations, it's the e to the x or e to the rx that played a certain role. Here you see that there's another kind of solution that plays a certain role called the fundamental solution. And for this, as I said, let's look for solutions with a certain kind of symmetry. And in fact, there's a neat fact. The Laplacian is invariant under rotations. What does that mean? It means that if, let's say, U satisfies Laplace's equation, and V is a rotation of U. So V equals to U of Rx, where R is a rotation in Rn. And if it's an orthogonal matrix, if you like, then in fact, if you calculate Laplacian of V, if you like in the new variables, then it equals to 0 as well. Again, what does that mean? It means suppose you have a certain solution, right? And you rotate it, then you get a solution, another solution as well. So sort of like this. You take maybe the first part, you rotate it, and you still get the solution. What does that suggest? It suggests that it might be useful to find solutions that are invariant under rotations. That, in other words, functions that if you rotate them, you in fact get the same function. And if you think about this, a certain kind of function that satisfies this are radial functions. Namely, if you have a function that just depends on how far you are from the origin, this actually is invariant under rotations. So, in other words, I want to find the following. Our goal is to look for solutions of the following form. namely u of x equals to a radial function, namely v, only depending on the absolute value of x, where v in this case is a function from R to R, is to be found. I guess R plus, if you like, is to be found. And here, to emphasize that v is a radial function, we write v of R. Okay. And not only that, once we found a solution of the following form, we also want to find a differential equation that v satisfies. And find a differential equation that v satisfies. Okay. Because why? It turns out that once we found a differential equation, it's actually easy to solve. And it's an ordinary differential equation because v has just one variable. And once we solve the differential equation, we can actually find u. U equals to v of absolute value of x. And by the way, this does not necessarily give us all the solutions, but as I said, we just want to find one at least for the beginning. Okay, and now, what is Laplacian of u? Again, that's ux1 x1 plus blah 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 plus uxn xn equals to 0. So, because we want Laplacian of u equals to 0, let's write the derivatives of u in terms of v. So, again, u is v of absolute value of x. So, uxi for any I from 1 to n equals to, by the chain loop, v prime of x, absolute value of x, times the ith derivative of absolute value of x. And you might say, how in the world can we differentiate the absolute value? Well, using the following trick. Note, what is absolute value of x, or if you want the length of x, in Rn, it's the square root of x1 squared plus blah 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 plus xn squared. So by the chain loop again, we can calculate that the ith derivative of absolute value of x equals to the following. First, differentiate the square root. So 1/2 times x1 squared plus xn squared to the minus 1/2 power. And then you want to differentiate the ith variable, which becomes, the only derivative that matters is xi squared, which gives you 2xi. Now, this looks very ugly, but we can simplify this. Because, in fact, this equals to 1 over x1 squared plus blah 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 plus xn squared square root times xi. But this thing on the denominator is nothing other than 1 over absolute value of x. So in the end, the ith derivative of absolute value of x is just xi over absolute value of x. So it's pretty neat. So in other words, this tells you that, again, the ith derivative of absolute value is just xi divided by absolute value of x, and by what we have here is uxi is v prime of absolute value of x times xi over absolute value of x. Okay. Unfortunately, we're not even close to being done because we found uxi, but now we want to do it again because ideally we want to plug this into Laplace's equation. So, what becomes of uxi? Let's use the product rule and the chain loop again. So let's first differentiate this sucker. So we get v double prime of absolute value of x, and then derivative of absolute value of x, xi, times whatever we have here, whatever it takes. Okay, plus, now product rule, you want to do this, and you want to differentiate this with respect to xi, with respect to xi. I know, takes a long time, but, I think PDEs, you have to be very patient, because those are fun calculations, but if you're not used to indices, those might be painful. But it's addicting, because you have this, now you want to calculate the derivative of absolute value. So xi over absolute value of x, right, like before, but then you're left with this times this. So it turns out this becomes a square. Okay. And then you still have the v prime of absolute value of x. And now you want to differentiate this carefully using the quotient rule. So we have the derivative of this, which is 1 times absolute value of x, minus, you leave that alone, and you're differentiating absolute value of x. So it becomes xi over absolute value of x divided by absolute value of x squared. Okay. And let's see if we can simplify this. In fact, we can, because we still have v double prime. Again, let's forget the inputs for a second. So v double prime times xi over x, absolute value of x squared, plus v prime, and then we have absolute value of x over absolute value of x squared, which simplifies to 1 over absolute value of x. And here we have something that looks very ugly, but you'll see in a second it becomes simplified. So xi times xi squared, divided by absolute value of x times absolute value of x squared, which becomes absolute value of x cubed. And you're having a bad time if you see a cube in your equation. But again, nothing is lost, because here what did we do? We calculated uxi, and remember, for Laplace's equation, we need to sum up things. Namely, we need to take this and add it from 1 up to n. So, let's do that. Laplacian of u, which becomes, I hate writing summation notation, but here it's very useful. That's the sum from 1 to n of uxi, which is the junk that we just found. That's the sum from 1 to n of v double prime times, if you want, xi squared over x squared, so absolute value of x squared, plus v prime times 1 over x minus v prime times xi squared over absolute value of x cubed. And anything that does not depend on I, let's just pull it out of the sum. So think of it as a big fire, and we're rescuing those poor v double primes and absolute value of x squared. So in the end, you have sum from 1 to n of xi squared plus, again, if you want, v prime over absolute value of x, sum from 1 to n of nothing, of 1 if you want, minus v prime over absolute value of x cubed, sum from 1 to n of xi squared. But here's the nice thing. What is x1 squared plus x2 squared up to xn squared? It's just the length squared. So in the end, you're left with v double prime over length squared times length squared plus v prime over length of x times sum of 1s, which just becomes n, minus v prime over length of x cubed times length of x squared, which is great. This makes the cube disappear. So here we have a bang and bang, and then we have a bangity bang bang. Okay. So in the end, you're left with, 0, which is, again, we want Laplace u to be 0, but this also equals to v double prime plus v prime over length of x n minus v prime over length of x. And remember, length of x is just r, just different way of writing this. So v double prime of r plus v prime of r over r times n. If you want times n minus 1, so this becomes this, and we want this to be equal to 0. Which is fantastic, because we took this really complicated PDE, Laplace's equation, and we turned this into an ODE, an equation of one variable, which we actually have hope of solving. So, in fact, let's now solve this ODE. So that was step 1. Now let's do step 2, but I promise it's not too bad, because let's rewrite this ODE. So now just to remind you, we have v double prime plus v prime over r times n minus 1 equals to 0. So v double prime equals to minus n minus 1 over r, v prime. Again, assuming that v prime is non-zero, because we don't care about constant solutions, we get v double prime over v prime is minus n minus 1 over r, which tells you that ln of absolute value of v prime equals to minus n minus 1 over r. Let's integrate that. Ln of v prime is minus n minus 1 ln of r plus a. So again, ln the generous makes another appearance here. And by the way, I didn't put absolute values because remember, r is a distance, which is positive. Okay, and then exponentiate that. So v prime becomes, if one, e of ln of r to the minus n minus 1 e of a, okay, which becomes r to the minus n minus 1 minus 1 times some constant. So instead of writing e of a, let's just write a. Okay, so, well, I'll do that in a second. So e of a times that, which tells you that v prime equals to plus or minus e of a r to the minus n minus 1, and a is a generic constant, so plus or minus e of a becomes another generic constant. Let's call it a r to the minus n minus 1. And then, look, this just becomes, the power rule, so all we need to do is anti-differentiate this function. So in the end, we get that v of r equals to, if you want, minus n minus 2a r to the minus n minus 2 plus b. Again, there is a caveat, so if you know it, don't say it, okay? But again, the a is a generic constant, so this also becomes a generic constant. Let's relabel this as a. So you get v of a, r, is a, r to the minus n minus 2 plus b. Except, just a little caveat, if n equals to 2, so if we're in 2 dimensions, this becomes r to the minus 1, which anti-differentiated gives you log. So it just turns out we have to do a little distinction. A little caveat. I love that word. It's like caviar, but in math, okay? So caveat, if n equals to 2, we get v prime equals to ar to the minus 1. So v of r is a ln of r plus v. So here's a summary in case you're still watching. Good job if you're still watching. So if you let v of r be in 2 dimensions, a ln of r plus b, and a in all other cases, a to the r to the n minus 2 plus b, n is greater or equal to 3, then in fact, if we let u to be v of absolute value of x, we indeed get that u satisfies Laplace's equation. In other words, this v of absolute value of x is so important that we call this, in fact, a fundamental solution. So definition, don't laugh, but fundamental solution like phi, so capital phi of x, which becomes minus 1 over 2 pi ln of absolute value of x for n equals to 2, and 1 over n times n minus 2 times alpha n, 1 over x to the n minus 2, n greater or equal to 3, this thing is called the fundamental solution to Laplace's equation. I did not break the chalk, it just fell down, okay? No worries, okay? Is the fundamental solution of Laplace's equation. And you may say, what the hell? What about those constants? First of all, alpha n is just the volume of the unit ball. In Rn. Okay, and if you want to see the explicit formula for that, check out one of my other YouTube videos. And why those constants? Well, it turns out those are the constants, I believe, that make the integral of phi equals to 1, at least over some region. And yeah, and you may say, why is this so fundamental? First of all, it provides us with a very non-trivial solution of Laplace's equation. So that's the first thing. Second of all, it turns out that with this fundamental solution, you can actually solve other kind of Laplace's equations, namely something that's called Poisson's equation. So let me just write down this little fact. Namely, if f is given, then the following function, so u of x, which equals to, in some people write it as f convolved with phi, I guess phi convolved with f, which equals to, if you want, the integral of Rn of phi of x minus y, f of y dy. If you take this function that involves f and a fundamental solution, it turns out it solves what's called Poisson's equation minus Laplacian of u equals to f. In other words, this process, convolution, allows us to go from the solution of Laplace's equation to the solution of a more general class of equations called the Poisson's equation. By the way, the proof of this is really cool. It involves a lot of advanced analysis, but maybe if you want, I can show this. Again, it's very long, but really cool. All right, and if you like that and want to see more PDEs, just let me know. And if you want to see other more fun math videos or more fundamental math videos, please make sure to subscribe to my channel. Thank you very much.